Hey physicists, steps for measuring the speed of the wave, for calculating the wavelength and frequency of standing waves, and showing that on the simulation are given in the write-up for the simulation. This will just give you a little introduction from the video end. Hey, so to figure out velocity, I need a couple of things. I need distance and time. Okay, so in the simulation, there's the opportunity to put in a ruler for our distance, and there's a timer here. Go over and here we are in the simulation. I've turned on the ruler here. Here's the timer, so I have two different ways of measuring my distance and time. And what I'll do is I'll give a pulse. We'll see what this looks like. Just blip there. Okay. You can see I have a pulse running from one end to the other. It gets to this fixed end, and I have the reflection on the other side of the line. I'm heading back to the beginning. I've set this to slow motion just to make it a little bit easier to calculate. I can see here the distance from my starting point here at 0 centimeters and my clamped end over here is about 7.5 centimeters. So the distance I travel every time my wave goes from one end to the other is 7.5 centimeters. So to start on the left side, over to the right side to the clamp and back over to the left side would be a total of 15 centimeters. If I did this several times, I would have a longer distance. Let me go ahead and just time this. Just an example of how to do the timing. You will have times of your own depending on how long you choose to make this measurement and your tension. So I'll wait till it gets back over to the left side. I'll wait till that leading edge here gets to the post and start. Okay. So it's going along 1, 2 lengths, so I've known it's got a total of 15. 3 lengths, that's 22.5. And finally along here, 4. Okay. Hey, so it looks like I have 4.78 seconds. Let me go ahead and enter that in the data. Hey, so I've repeated these measurements. I changed the tension, so I ended up with a little bit different time than I originally showed you, but just this will show how it's done. So I did stick with 30 centimeters. It took me 6 seconds to figure out the speed I just take. Again, let me get this writing again. Remember that our velocity is equal to our distance divided by time. So 30 divided by 6 is 5 centimeters per second. Let me do this next one. 30 divided by 6.1 seconds, I get 4.9 centimeters per second. And this last one, 30 divided by 5.9 seconds, I get 5.1 centimeters per second. Now for the average, I'll just add 5, 4.9, 5.1. That's equal to, what is it? That's equal to 15. I'll divide by the number of entries, 3. And my average is 5 centimeters per second. I'll put that in here, 5 centimeters per second. Right. Let's scroll on a little further down. What are we going to do with that? Okay, hey, we're going to make a prediction about the, let's see, our standing waves. Hey, so think back to your homework assignment where you had the two kids jump roping and you were figuring out wavelength and frequency data from that. Hey, so we calculate our velocity in the above step as being 5.0, and I'll change this unit out, centimeters per second. And with a wave, as long as the medium stays the same, and that would be, say, the string and its tension, the speed of a wave does not change. So I can put that in for all my units here. Okay. Hey, so what about the wavelength? Let me pause this for a moment. For our first harmonic, that tells, hey, so if we have one bump, that's 7.5 centimeters long, and it takes 2 bumps to make a wavelength. In this case, our first harmonic with one bump would have a wavelength of 15 centimeters. Go ahead and write that in. Okay. 15 centimeters. Hey, for 2, and if we have a distance of 7.5 centimeters from one to the other, and we have 2 bumps, okay, that means that each bump is 3.75 centimeters long times 2. That's going to tell us the wavelength is 7.5 centimeters. Okay, so for 3 bumps, okay, and having it 1, 2, 3, I have 7.5 centimeters divided by 3. That tells me that it's 2.5. Get this over here. 2.5 centimeters per bump times 2 is the wavelength is 5 centimeters. 5 centimeters. I'll let you finish out the rest of this. Hey, what about the frequency? Hey, we know that velocity of a wave, listed up in the reading, is the wavelength times the frequency. So we could rearrange that to say that, hey, the frequency is equal to the velocity divided by the wavelength. We have a velocity of 5 meters per second. We'll divide it by the wavelength of 15 centimeters. Okay. That tells us that the frequency is 0.33. The centimeters will cancel, so we have seconds on the bottom, hertz. Let you figure out the rest for yourself on those. Let me go ahead and pause this for a moment. Now for my wave, I found that the fourth harmonic's frequency was 1.32 hertz. So I set that here, setting it at 1.32 hertz. And I have it slow motion, make it a little bit easier to set up. And I'll allow our oscillator here to rotate 4 complete times. I'm anticipating I'm going to have 4 bumps in here because it'll be the fourth harmonic. Means I'll have 2 waves going and 2 waves coming back. Because I have a total of 4 waves, I'm going to need to oscillate this or allow it to go through 4 complete revolutions. Okay, and here I go. So 1, 2, 3, and coming around, and 4. Okay. Hey, if I'm a little bit short of coming all the way back to my starting line, that works out well. I can use this little bump here to go ahead and set it right on that center line. Hey, once I have 4 complete revolutions on this, I pause. Okay. I change the amplitude and the frequency to 0. Okay. Then I go ahead and start my simulation. Why do I set the amplitude and the frequency to 0? Because I want this end to stand still, because that will allow the waves to bounce back and forth from that end. Let's see how it goes. Yeah, I can see I've established a standing wave. If I want to find the nodes, 1 here, 1 here, 1 here, 1 here, 1 here. My antinodes, 1, 2, 3, and 4. So I know it's the fourth harmonic. You can go ahead and pause this at some maximum amplitudes, take a screenshot at 3 different harmonics, insert that to the assignment. The other thing was just at the end it says, hey, once you have the standing wave going, go ahead and adjust the tension, see what happens. To give you a little bit of a hint as far as what happens there. Notice the frequency of the oscillation. I move this up to a higher tension, much like a tighter tension on a guitar string. Notice what happens. The wavelength stays the same. Length of each of the harmonics stays the same, but we increase the velocity, so we had to increase the frequency. And you can probably figure out if I reduce the tension, not as much force, therefore less acceleration, it doesn't go back and forth quite as much. Okay, hope this helped with your simulation.